Bismillahirrahmanirrahim. Dear students of Mathematical Techniques for Boundary Value Problem, MS first and third semester. Today we will discuss our fifth online lecture. In our previous two lectures we have studied two examples and find their solutions with the help of staining method and Lindstedt-Poincaré technique. And we saw that in case of singular perturbation, when a secular term arises in the solution with the help of regular perturbation method, then we will use the method of staining coordinates or the Lindstedt-Poincaré technique, which is basically to expand both dependent as well as the independent variable. In today's lecture we will consider the previous example, redo the previous example by using the transformation tau is equal to omega t. In our previous lecture number 4, we have used the time variable t is equal to s into omega, but this is another transformation tau is equal to omega t, where we have to expand omega as well as the dependent variable u. Therefore we will introduce the transformation tau is equal to omega t, where omega is a constant that depends on epsilon and which needs to be determined, और इसको हम फाइंड करेंगे. सबसे पहला स्टेप आपको पता है, we have to use the chain rule in order to transform our original derivatives from t to tau. Therefore using the chain rule, आपको पता है d by dt को आप लिख सकते हैं d tau by dt into d by d tau. Therefore d tau by d t will be omega, and this becomes omega d by d tau. Similarly, the second order derivative d2 by dt square will be equal to omega into d2 by dt d tau. Again chain rule use करेंगे तो आपके पास omega square d2 by d tau square आ जाएगा. Therefore equation 5 was our previous example that was solved in our previous lecture. Then that equation जहाँ से हमने example start की थी, basically ये हमारे पास वो equation है u double dot plus u plus epsilon u cube equal to 0. ये हमारे पास equation थी. तो अब जो u double dot है, that is simply omega square u double prime, where prime is the differentiation with respect to tau. याद रखें जो differentiation with respect to t है उसको डॉट से हमने डिनोट किया हुआ था, और जो differentiation with respect to tau है उसको हम यहाँ पे हम प्राइम से डिनोट कर रहे हैं. तो सिर्फ पहली टर्म चेंज होगी which becomes omega square u double prime, बाकी u और epsilon u cube are unchanged because इनमें derivatives involve नहीं है. Therefore our problem reduces to this highlighted equation omega square u double prime plus u plus epsilon u cube. Next आपको पता है कि हम u के लिए standard straight forward expansion use करेंगे, which is u naught of tau plus epsilon u1 of tau, and epsilon के लिए भी हम expansion use करेंगे a specific form, क्योंकि आपको मैंने बताया था कि जो ओमेगा नॉट है that is always taken to be 1, वो यहाँ पे हम उसको 1 ही लेके चल रहे हैं. Therefore for omega our expansion will become 1 plus epsilon omega 1 up to so on. Now putting these two equation 19 and 20 in our equation number 18, which is the governing equation, after using the new transformation, our equation becomes this one. ये हमारे पास इक्वेशन बन जाएगी। Now equating the coefficients of epsilon power 0 and epsilon power 1 from equation number 21, we get the following two second order ordinary differential equations in u0 and u1, which are given by equation number 22 and equation number 23. u0 double prime plus u0 equal to 0, u1 double prime plus u1 equal to minus u0 cube minus 2 omega 1 u0 double prime. First we will solve equation 22 for u0, and you know that its general solution is given by u0 is equal to a cos tau plus beta, where a and beta are the constant. Now putting the value of u0 in equation number 23, equation number 23 becomes equation number 23 is given by this highlighted equation. Now we have to solve this equation. Here we have utilized the trigonometric identity of cos cube of theta, which is now turned into cos theta and cos 3 theta. यहाँ पे ये जो सिंप्लीफिकेशन हमने पहली एग्जांपल में भी की थी, आपको याद है, cos क्यूब थीटा पे हमने डिमोव्स थ्योरम की मदद से इसको sin क्यूब थीटा हो या cos क्यूब थीटा हो, यू कैन राइट इट इन टर्म्स ऑफ cos थीटा एंड cos 3 थीटा. एक्चुअली cos 3 थीटा पे हमने ये फार्मूला लगाया cos थीटा प्लस 2 थीटा करके, तो यहाँ से आपके पास एक टर्म cos टाउ है, यहाँ से cos टाउ आएगा, इन दोनों को आप ऐड करेंगे तो आपके पास ये पहली टर्म आ जाएगी cos टाउ प्लस बीटा, और सेकंड टर्म जो आपके पास आएगी दैट विल बी with cos 3 theta, which is 3 into tau plus beta. Now the solution of this equation 22. Once again, this solution can be determined with the help of undetermined coefficient methods. First you have to find the complementary function and then you will find the particular solution. Therefore, the final value after adding u0, after adding u1c and u1p, that is the general solution of u1 is given by 26. And now in order to eliminate the secular terms, आपको पता है कि इस मेथड में जो सबसे इम्पोर्टेंट स्टेप है हमारे पास, that is we have to eliminate the secular terms, and you can see that the secular term is appearing in first term for tau sin tau plus beta, and for infinite tau this term is not bounded. Therefore we can take the coefficient of this term, which is 2a1 2 omega 1 a minus 3 by 4 a cube to be 0. जब आप इसको 0 लेंगे, now finding the value of omega 1 की जो वैल्यू है हमारे पास वो आ जाएगी 3 by 8 a square. Therefore u1 after putting the value of omega 1 is given by equation number 28. And now you can see that the secular term which was appearing in u1 is eliminated. Hence the two term expansion is given by u is equal to a cos omega t plus beta, equation number 29, plus epsilon over 32 a cube cos 3 omega t plus 3 beta, where omega is given by 1 plus 3 over 8 epsilon a square, which is again similar to equation number, the solution 16, which we have obtained earlier. Next we consider another example, which is u double dot plus omega naught square u plus epsilon u dot square. Here the dot denotes the differentiation with respect to t, and you are asked to determine the first order uniform expansion by using the Lane-State-Poincare technique. With the help of this method, let us define omega, which is let us introduce tau, which is omega t, omega naught plus epsilon omega 1 up to so on into t. Now changing the derivatives from t to tau, you can see that the second order derivative will be changed to omega naught square plus 2 epsilon omega naught omega 1 up to so on into u double prime. ये हमारे पास first term आ जाएगी. This is for second term, and the terms on the right hand side will take this form. Now letting the regular perturbation, regular or straightforward expansion for the u in terms of in powers of epsilon and u naught and u1 ui's as a function of new independent variable tau, we get equation number 4. Now putting equation 4 in equation number 3 and equating the coefficients of the like powers of epsilon, we get these two systems given by equation number 5 and 6, u naught double prime plus u naught equal to 0, and equation number 6. We know that the solution of equation 5, the general solution is of equation 5 is given by u naught a cos tau plus beta. Now putting u naught into u1 equation for u1 will take this form. यहाँ पे हमारे पास जो है वो सिंप्लीफिकेशन हमने की है. जो हमारे पास ट्रिग्नोमेट्रिक आइडेंटिटीज यूज़ होती है उनको आपने यहाँ पे सिंप्लीफाई करना होगा. नेक्स्ट यू हैव टू एलिमिनेट द सेकुलर टर्म्स. और यहाँ आप देखें, आप इस इक्वेशन को सॉल्व किए बगैर डायरेक्ट यहाँ से भी सेकुलर टर्म को एलिमिनेट कर सकते हैं. अगर आप देखें तो हमारे पास जो सेकुलर टर्म अपीयर होती है, दैट इज now the secular term appears because of the first term on the right hand side, which is over here. ये आपके पास जो टर्म है ये अनबाउंडेड हो सकती है. Therefore we have to equate the coefficient of this term equal to 0, and if you put the coefficient of this term, which is 2 omega 1 over omega naught a plus 1 over 4a cube equal to 0, and from here we can get omega 1 as minus omega naught a square over 8, and hence putting the value of omega 1 instead of in our expansion for tau, the solution in terms of u will be given by a cos omega naught 1 minus epsilon a square over 8 t plus beta up to so on. So this is the solution with the help of Lane-State-Poincare technique for the given differential equation. That's it. Thank you.